recent PGP problems aren't with RSA, they're with elsewhere in the...
They were with symmetric cryptography. So if you remember Cbc Mode of Operation, it was specifically a chosen plain text attack. So it was because you knew like the first, it's like a message started with content type blah, then you could inject essentially like a tag that ignored some ciphertext block, and then because essentially it has like a dependency via the XOR, and then it made sure to add a tag that all the text after this slash gets sent to this address. So that's called exfiltration or just data extraction, if you want to call it that way. That was with symmetric encryption. TLS one, that was when we were talking about Poodle. And this is when we had, instead of having like a secure key agreement, it downgraded, like essentially, like the key agreement was fine. It downgraded the encryption from here to here to CBC, which was broken with a padding oracle. So we talked about padding oracle, about asking the oracle, hey, are these bits okay? And then we keep checking bits and bits and bits based on the PKCS 7 padding. So we keep asking that oracle, and it's like, hey, is this okay? Until the oracle essentially decrypts a bunch of the stuff for us. So what happened with Poodle is that they wanted to make a padding oracle. So like for compatibility reasons, TLS is like, it has a set of, it's not one algorithm, it's a set of algorithms. Usually for backwards compat. So somebody on a lower version of TLS before could downgrade to these insecure ones. So the attacker would go, hey, I'm sorry, I only know AES CBC. Like, could we communicate? And like, but this would be a man-in-the-middle attack. So a guy would be trying to normally connect, and then the man in the middle goes, by the way, server, I only know AES CBC. And the other guy also knows AES CBC. So it seems like the server is saying, oh, I only know AES CBC. So then they both get downgraded, and the man in the middle, now he can break CBC via the padding oracle. And that was the issue essentially with Poodle. But TLS usually establishes a shared key, but it's a session key, so it's not one for your whole connection. It changes eventually after a certain number of messages, and it is authenticated encryption. But you get a key agreement, and then part of the reason, so you might think, why is it that they're not just using asymmetric cryptography all the way? And it's because asymmetric cryptography is sometimes 1,000 times slower than symmetric cryptography. So that's why you go out of your way to exchange a key. Technically, you could. I mean, if you think about it, it's not necessarily any more insecure to use asymmetric cryptography, get a key pair, and then just transmit all your messages that way. But if it's significantly slower, and I'm talking about the realm of the thousands, for example, for RSA, especially for large keys, then we know symmetric cryptography is really fast. So we use our asymmetric cryptography to get, establish essentially a shared key. And then with that shared key, we use that for symmetric cryptography. That's how TLS does it, in a little bit more of a complicated way. There's concerned with forward secrecy, so making sure that all previous keys don't compromise the security of your next keys because they're session keys. There's more to it. The implementation is very complicated, but that is essentially the heart of TLS. It's key exchange plus symmetric cryptography. Okay, so actually, first let's consider the fact that signature takes a private key and outputs a sigma, and verify takes the public key, the message, and the sigma, and it gives you a boolean. It gives you a verification. Where I was going at, the reason I tabbed out is I look for signature in what's it called? Sig key pair. Let's trace the types, because we are concerned with programming to some degree. I think, not sure, with ECDSA. So this is by the way, this is like a digital signature SHA-256. So we're gonna get to why we hash it, by the way. But this is SHA-256, so a hashing function with the digital signature algorithm using elliptic curves. So this is an ECDSA signature, which essentially takes, signature API, play with the types. So we call it a certificate signer. So first let's go with a signer. This is the same thing. Now this is the same notion. We have so we have a hierarchy type, our effect type. We have an algorithm A, and we have our public key, which is a hierarchy type, which takes one type parameter, and private key which is also a higher kinetic type, a star to star. And I mean, the reason why we want to make them higher kinetic types is just simply so we can parameterize them on the algorithm and fail at compile time if we give it the wrong key. That's all. Nothing stops you from being an idiot and coercing it via casts. But I mean, code not written by a madman will benefit from like the compile time safety this sort of thing does. And I'm not asking you to use TSEC. I'm just trying to show you why I came to these design decisions. All it is in TSEC, the only thing TSEC tries to really do is state this as much like a law as I can in the very formal definition without bogging myself into storing exceptions on initialization and using the compiler to make sure that we pass the right length keys, right? We're trying to leverage the compiler because then we don't have to consider the fact that it might throw an exception if you give it a wrong length key. And rightfully it could, but if you could stop it, imagine if you could stop it at compile time forever giving it the wrong length key, then you would want to, and then you wouldn't even have to consider that case. That's kind of how you get to sign these things. How you get to, like, if you're designing a cryptographic library, be it in Haskell or be it in Scala, how you can consider abstractions in general over this. And the only bad thing, I guess, is that you have to. A lot of these are pure functions, but you have to, if you are abstracting over like FFIs, then you kind of need to make the effect type not just identity.
Also for ECDSA, your ephemeral private key needs to be random.
Yeah, I mean, but like that. Yeah, I guess that's true. Like you do need the. But I mean, like I guess what I'm trying to get at is that my signer. So actually, this is not the same as the thing because I actually have key gen or key pair. So essentially, I have a key pair class. Sig key pair. Oh, okay, navigation is terrible. But my point being that essentially, technically and done properly, only the generator needs to be wrapped in I/O, because the generator is the only part that actually holds state. You don't necessarily need the signature. The signature is not concerned, right? I mean, like you can generate, you can manage your impure state in I/O for your generator functions. But when you're applying the function, when you already have the key, you don't need to work in I/O. It's a pure function.
ECDSA, there's the random type.
Yeah, well, okay. For ephemeral ECDSA, yes, but for the regular like SHA, like yeah, you're talking about ephemeral ECDSA, yeah. So yeah, in this case it's good. But I actually abstracted not just for ephemeral ECDSA, because when I wrote that I was not even that knowledgeable on it, because I wrote this last year, and then it turned out that it's good. But anyway. And I'm sorry if I haven't been programming enough, but mathematics is cool. So anyway, we can, again, with the same notion of reusing what we did before, we can use RSA as a digital signature scheme. And it's super easy. Just imagine like what we did before for RSA, except that like instead of wanting to encrypt it and decrypt it for the sake of, secrecy, we just put in the ciphertext and we verify that it's the same as the plaintext. Same thing. So it's literally just applying RSA, except it's RSA, except your message is in the clear. So you give your message with this, and you're verifying RSA. But the main problem is that this doesn't really scale very well. What does anybody have an idea why wouldn't? Like why wouldn't it scale, I guess? Sure, go ahead. Yeah, so that exactly. So your signature scheme is going to be as large as your data. Then again, sorry? Well, okay, you are like ahead of everyone else, but yes, that is literally what the next slide was about.
I just thought that was like the default way people did stuff.
No. I always start from the bottom and go up. This is like this is the never do it. Remember CBC Mac? Never do that either. But this is the way you like. So you were right. You use a hash function, and instead of operating on m, you operate on the hash of m, and then you verify on the hash of m. And then operating on the hash of m instead of m makes it so your hash is now a fixed length, and you can deal with arbitrarily long messages. And you were using essentially like the decompression, the properties of hash functions of truncating like our input into a fixed length size. This is where we're. So in this exercise, this is literally I'm not gonna do it, but I'm gonna show you what it was. Very similar. So very similar thing. Instead, we had something that was a transaction. So and every transaction had a from, a to, a quantity of some amount that we were transferring between users, and then it also was signed. It had a signature. It was signed by the from person. And by the way, this is very weakly typed. It's from string and to string. So you wouldn't do this, but it was just faster to write it this way. And also, this is not exactly correct. I mean, usually for transactions, let's say for Bitcoin, you don't even need. You might not need that much information. There is information on the transaction, but you can mostly just do with the information of the signature and the public key. And you can verify this. So if we have, so this is the signature created with a private key, we can verify this with the public key of the person that created this transaction. The sender, by the way, this is not a receiver, but this is only a one-way. And then we repeated the same concept for Dogecoin, where we were creating a Doge chain of transactions instead of, I could have parameterized Doge chain, but I didn't. But we could create a Doge chain of transactions because these transactions, now with digital signatures, all we have to do is just, we can hash them and then we can verify them. But the verification step, we only need the verification step if we want to know how much coin a particular person has. It's not going to impact how we actually calculate our shitty blockchain. But again, this actually, what I had that as an exercise is another full to tree function, which was essentially the same. But then I also had one exercise which was traverse the Merkle tree, and then we would deserialize, so we would store these transactions now as a JSON, and then traverse the Merkle tree, and then try to figure out how much a user has, how much coin a user has, knowing an initial amount by subtracting or adding the amount that they got sent or received. That was the whole exercise of get total for user. So you would have a user. And then you with some initial amount, and then based on these transactions, we would figure out how much they actually have. This would have been a cool exercise, but it's 4:42 and it's really time consuming. So let's get to elliptic curves, which is the coolest part. So elliptic curves are a set of solutions to the Weierstrass, I think that's how you say it, the Weierstrass equations. So it's essentially set of solutions to this equation. So y squared equals to x cubed plus ax plus b, in such a way that the coefficients ax and b hold this constraint, which we call the discriminant. That means a, like 4a cubed plus 27b, actually that's b squared, not b cubed. That's a mistake probably made from copy pasting. That's b squared. I'll make sure to make the little corrections for the integer thing and the other thing in my updated slides. But this is b squared. And I think I might have written it down properly somewhere else. Here you go. Yeah, I wrote it down properly here. Whoa. Okay. Yeah.
Are these all rational numbers? X, Y, A, B. What's the name?
No, they're integers. Yeah. So the nice part about elliptic curves, which you already know probably, is the fact that elliptic. Yes.
I'm sorry, you want the coefficients to be integers, but x and y can be interpreted as.
I mean, they're functions on integers. It's just a mathematical function. It's a function on integers.
Well, we say curves, so I mean the
I'll get to that.
Are
So you have to a little bit. It's integer valued. So you want to consider the curve. Yeah, I mean if you want to consider in the rational numbers, yeah. But if you can treat the elliptic curve as an integer valued, what's it called? Domain codomain.
Well, and more importantly, the elliptic curves as real numbers will make it easier to conceptualize, but when we translate this to encryption, we do it over a finite field.
Yeah. Well,
I mean, you can have a finite field over the rational numbers, but it's not going to be, what's it called? You're not going to have the same nice properties of what's it called? Of inverses as easily. It's going to be a mess. And for example, you're not going to have, what's it called? Difficult to find inverses in certain scenarios. Because for example, for a rational number, you could just do 1 over the number, and then you have the multiplicative inverse immediately. So problems are just not as hard when they're not integer valued. But So, oh yeah, I mean, the second paragraph of this, I'm gonna skip it, but it just talks about the fact that elliptic curves are really nice because they have these algebraic properties to them. So very similar to everything else we just saw, elliptic curves can do, which is really nice. But we have to think about elliptic curves differently, right? Because when we think about a curve, our basic notion from calculus or from wherever else, just basic mathematics that you interacted with graphs, you usually think of points like an xy on a coordinate plane, right? And then if I want to add x1, y1 to xy, usually it's just x1 plus x, y1 plus y, right? This is usually usually how we treat it. This goes away. Oh, this goes away for elliptic curves. This is not how we treat elliptic curves. Elliptic curve addition is actually defined as simply drawing. So we have two points. They can be distinct or non-distinct. We can talk about when they're not distinct. So we take 2 points, P and Q, that are on the curve, and then we draw a line through it, a line through P and Q. And then they intersect, and that line intersects the curve at only one more point, which is R. That R is the result of our P and Q. That is it.
Wait, and does R always be neutral?
Sorry?
And so R will always be some integer point? Like
If
some
it is,
technical
you
property?
just keep following the line over the modulus
Yeah.
until you find one.
Oh.
Well, I'm not even getting to modulus yet.
Oh.
No, but
And
you
that
are correct.
also will eventually intersect, I guess?
No, it does. But hold on.
Sorry, go ahead.
We will get there. That's literally the next slide. But so what happens if we have some elliptic curve here, right? So what we have P is xy. So what happens if, and by the way, if we're adding P to P, we just simply consider the tangent to the P. You guys know the tangent, and sorry?
So, how do you always know okay, I guess we'll get to that later.
Yeah, we will.
Just assuming the fact that as a third point, that'll be the result of addition.
Yes, but we are getting there. So usually when you add P to itself, the line is a tangent, and we consider it still crossing the curve at 3 points, just P is 2 of them. But now what if, so remember we have x, y, what if we invert y, right? What if we invert y? So let's call this negative P, x, negative y. Turns out this doesn't cross anything because this is essentially a vertical line. And then mathematicians cheated because we can. Actually, I'm not even a mathematician, but they can. And we call this point a point in infinity, denoted by O. Like, oh, they just did that. But that's a really bad joke. But it's actually true. That's exactly what happened. And you consider essentially that point as your identity. So now this is your inverse P. Actually, and yes, it does behave monodally, and it does behave nicely, like, what's it called, like a field. If you take the modulus, of course. But now,
Is that the usual projective geometry point infinity?
I'm not sure. But ish. I mean, the only reason I'm saying ish is because the definition of addition is a little bit more involved than like what I showed you. Remember, because it's defined as a tangent. There is an efficient algorithm for it, but it's not just your regular add the coefficients of x and y. So the nice part is that, because we created this fictional point in infinity, now P with P prime, which is actually the inverse of P, we set it to this O and we called it a day. And the nice part about this is that now it can act like an algebraic identity. So when we add the infinity point to P, it works just like an identity element. And multiplication defined on elliptic curves is, it is this way in integers, but we don't consider it this way usually, but it is just repeated addition. Yes?
Scaling might be a better word for that.
Or
than
scaling.
Multiplication, because we're not multiplying 2 points.
But remember that we call multiplication not the act of multiplying like an integer. We talk about multiplication as the operator on fields.
I see. Oh, yeah.
So the operator itself is called, like one of them is called addition, one of them is called multiplication.
Sure.
Right? So that's why we call it multiplication in this case. This is just field notation, but you're right. You could think about it as scaling. And it happens to be commutative and associative, so it forms an abelian group. And then what happens is, what if we wanted to get a field out of this? Well, what's nice is that we can actually have an elliptic curve over a finite field f of p, so long as like said p, haha. Anyway, so long as that we alter how we consider what a legal point is in terms of that p. So what does that mean? And this is like a super simple exercise that we will do together. And it's that, let's say we have, oh man, I would really love a random curve. Let me look in the textbook. I'm just going to pick a... Sorry? You know what? Okay, well, you know what? I'm just going to pick up an easy curve.
It's got small coefficients. That's why.
Okay, wait, hold on. No, not easy DLP. I just want like a really easy curve. What is it? 2y dx. Okay, so let's consider y squared minus is equal to x cubic minus 3x. What's it called? Plus 3. Okay. So let's consider this easy curve. All we have to do, so I'm going to write it pretty, but while I do that, I'll talk. So this still has to, so remember, this means that the properties of, so minus 3x plus 3. Now we know that for a cubic, so this is a, by the way, this is a, this is b. So for a cubic plus 27 b squared should not be 0. So we can compute this one really quickly. 4 times 27 plus 27 times 3, which is what? Okay, this is clearly not 0. Oh wait, no, sorry, this is negative 3. Negative 3.
3, that's...
Negative 27.
Yeah, A is a minus 27.
Yeah, but I mean, but actually, okay, so this is minus 27, but you see that this is 4 and this is 3, so you're going to get one of them. So you're going to get minus 27 here.
3.
Sorry?
That B squared.
Oh yeah, you're right, this is 9. But well, anyway, what I'm saying is that they don't cancel out.
I see, yeah.
So they are going to...
27 times 5.
They're gonna satisfy the discriminant. My shitty math. Thank you for correcting me on that. But okay, so all we do to create this curve over finite fields, x cubic minus 3x plus 3, all we do is that we ensure that when we plug in an x under the finite field, it is a square in that field. So what do we mean? So let's consider 11. So now we're going to call it, this is the notation. So we're going to say the elliptic curve E, we denote this thing as E. Under the finite field of 11. So let's just try a random number. So essentially, we're going to have 1. So we're going to see, so 1 minus 3 plus 3, is that going to be a square? Modulo y. So let's see. So this cancels out, you just get 1. And then of course you get plus and minus 1. So that means that, so of course, like this is a, what's it called? This is mod 11. This is a square mod 11, right? 1 is a square of itself. So we take the plus and minus. So that means we already have, so we establish our first points in our elliptic curve. 1, negative 1, 1, 1. Actually, you have to start with 0 to be fair. So let's do 0. You have 0. So we do, this is just 0. So no, it's not a point.
No, it's 3.
Sorry? Oh, wait. Oh yeah, you're right, it's 3. But 3 is not a square, so we're good. And then we can go on like this, by the way. So we keep plugging in this function, and then we sort a list. We have a list of points And these points all behave algebraically. That's the nice part. So when we add any of these points, we're always going to get a point in the same set. And because of that, then we can define the ECDLP, the elliptic curve discrete logarithm problem, which is the same as the discrete logarithm problem, except over elliptic curves. So it's the same thing. If you guys remember, g to the x is congruent to h modulo p. Then imagine that we what's it called? We instead of g, we picked some arbitrary point. We would have, let's call that point p. X times p is congruent to some point q. We use p and q usually for elliptic curves, and then what's it called? In e of f of p. And essentially, this is the discrete logarithm problem immediately for elliptic curves. And everything that we made, everything that we established for asymmetric key exchange, it applies there. So like elliptic curve Diffie-Hellman, same thing. So if I were to I can write out elliptic curve Diffie-Hellman for you, but it's gonna be everything you already know. So instead of knowing, so remember for Diffie-Hellman we know the generator G, and then we know some, what's it called? We know some prime P, right? These are our public parameters. Now instead we know the point P. This is small p, by the way. Now we know big P, which is some point. We know elliptic curve under some finite field. And then we do the same thing. You know, this, and anyway, what I'm getting at is this guy will pick some exponent n, this guy will pick some exponent m, they will talk to each other, they will do n times m, and then they will generate a shared key based off of that. Yes?
P, the point has to be a generator, right?
Yeah, but I mean, actually, for yeah. So in elliptic curves, that has a really nice property. There's not, because in elliptic curves, we're not thinking about powers anymore. We're thinking about power, like essentially multiplication in terms of, or powers in terms of just like repeated addition.
Can you write out so an elliptic curve over a finite field, is that itself a field? Or am I misunderstanding?
No, I mean elliptic curve over the finite field. Yes, it is. It forms a finite field as well.
It forms a finite field.
So we use the modular arithmetic properties of the finite field to calculate which points are in the curve, and then after that we don't actually have to do anything else, in the sense that once we have the points, running the addition algorithm, I'll show it to you mathematically, but it's not. I mean, it's literally just number crunching. I mean, the simple one is just number crunching.
So does that mean like we're literally dealing with the modulus, or that we're just using mod as our like analogy for finite fields?
Exactly. By the way, this right here.
Literally a modulus.
This is, yes, literally a modulus, but this is the elliptic curve addition algorithm. So if P is the empty or P, or like, then you know P1 P2 is P2. So just basically, you know, if it's the empty element, it's obviously the other one. And what's it called? Then otherwise we set the 2 points. Then we define some parameter called lambda. The first one is, this is just a slope if P1 is not the same as P2, or some other quantity here. And then we compute x3 this way and y3 this way. But we don't even have to take the, what's it called? We can't take, when we take the modulo over this calculation, all over x and y, it's gonna always be in the same subset, in the same set. So that's pretty cool. And essentially, the ECDLP means that we can form elliptic curve digital signature algorithm. I didn't cover DSA, but DSA is not too complicated of a construction. But it's just another algorithm where you encrypt the hash. Sorry, when you hash the message and then you actually apply, like, it's just a very specific way of constructing. It's just another one of the asymmetric signature like algorithms that is based off of the DLP. And you can construct it with elliptic curves. Anything that you can construct that is essentially based off of DLP for hardness, you can construct in elliptic curves. But what we like about elliptic curves is, number one, no integer factorization. So no, not just the fastness, but the fact that you don't have the issue of integer factorization. And we have broken integer factorization so many times. And sieves are terrible. And there is no index calculus as well. So when I talked about index calculus for the DLP, then there is no index calculus, because index calculus is actually defined computationally in a fast way, where you essentially get a bunch of quantities of like very similar to the relation building thing, but you actually do matrix reduced row echelon form. So you do a bunch of matrix multiplication in mathematics, which, as you guys know, AVX instructions means really fast on a PC. And we managed to factor out, what's it called? We managed to factor out the DLP a lot faster. So elliptic curves don't have this problem. But then again, elliptic curves are not new, but newer in the sense that it's not straight up proven that it's harder. It's just thought to be harder, because we have broken RSA in so many different ways that we don't have to, we are not concerned with, we try to avoid it if we can, because the only way RSA is secure is, again, no B-smooth numbers and no numbers that are easy to factorize via difference of squares. So now you have a little issue. And then you also have an issue that if you don't pad, so now you have to also add padding to your RSA, because if you don't pad it, then you can solve it via the Chinese remainder theorem. And I'm sure there's still websites using JavaScript that are using unpadded RSA. And CryptoPals, the crypto challenges that I mentioned earlier, one of them is like breaking unpadded RSA via the Chinese remainder theorem. But this is I guess where it's 5:02. I think I can take questions and we can just discuss stuff. But this is, I can cover other constructions if you guys would like ECDSA or DSA. But here is where my presentation ends. You have a question?
Yeah. Well, okay. Sorry to just keeping on the same point, but
yeah.
So the field, the elliptic curve over a finite field, is itself a field, and
yes.
So
it behaves like a field. Yes. So yeah,
the
it is a
elements
field.
of the field are the points.
Yes.
And then what does it mean to multiply 2 points together?
It just repeat okay.
Well, so adding, I get it's the addition operation defined, but what does it mean to take a point and multiply it by its point? So
You don't.
You don't
No.
need multiplication in the field?
Well, you need the scaling, I guess.
You only need scaling.
I just was thinking. I just went to linear space, vector spaces in my head, and how
So
we don't consider multiplication in that same way. We consider multiplication.
For field multiplication is really like a scalar times the element.
Yeah.
Got it.
you say multiplication.
But
n was an integer.
yeah. But I mean, in general, I mean, when we're talking about some coefficient of a times some coefficient of what's it called, a b, we can always restate multiplication in terms of addition, right? I mean, that is how it is defined. So that is simply what we do for elliptic curves. We essentially rewrite it, but now we avoid all of the integer factorization issues.
But
And
that's why we don't have a field anymore, because the field requires it to be an associated
I think there is.
over 2 arguments in the same field.
So I think then you're probably. I think you're right.
Yeah.
So I don't think you have a field, but you're working.
But it is over the field, 2.
Yeah, is an elliptic curve over a field in itself? Yeah, you're right. It is not defined for multiplication, so it is not a field.
Okay, but it has the addition forms a group, an abelian group. And then it has this extra scaling thing.
Yeah. But we can define multiplication for a particular element in terms of that. Yes. So we can define NP, like multiplication for P, but we cannot define multiplication for P and Q.
In vector
Yes.
spaces, we call the domain that the scalar is drawn from. We call that a field. In vector spaces.
Yeah.
P times Q would be kind of cool to
Yeah, if you
make
could.
your own ad hoc kind of
Satisfy the laws,
transformation.
though.
And then
It
you.
might not satisfy that many laws. But
I mean, you could be IOTA and then roll your own crypto that way until someone breaks it.
it would probably, yeah, sure. Then
But-
you discover something.
Possibly, yeah.
If we have time and you're prepared enough, do you want to talk about something else, like zero knowledge proof or lattices.
I did not prepare much about that, to be honest.
And we're
And do you want me to live code for half an hour in regards to digital signatures? I mean, the thing that I was gonna live code is I was gonna live code like a web app, but I don't think half an hour is enough. What I could do is that I could live code the digital signatures blockchain thingy. So we could do that. That one's very Scala specific, in the sense that because we are serializing and deserializing JSON, so I could do that. But yeah, I mean, I blazed through other topics. So, I mean, if there's anything you would, so I like the thing is that even if I could talk to some degree about lattices, I don't want to mess up because I am not prepared. Like I did not consider lattices. I did consider it initially in my draft, but when I was talking through this, we really kicked it into gear in the past like 2 hours. But if you saw like the first parts were a lot more in depth, and if we kept that depth all the way through, we would have never made it to elliptic curves. So we had to truncate some proofs and hoped that we got it before 5:30. Yeah.
Could you talk about other sort of interesting design decisions you made?
Yes, actually. Okay, cool. Yeah, we could do that. We could talk about essentially TSAC and how I created essentially a lot of the primitives. And we state a lot of these things in terms of laws. Or sorry, one of the first things I said in this lecture is that a lot of these things are not always laws. Why? If you guys remember computational security, for example, it's defined probabilistically. So it's not a law. I mean, formally, you cannot have a law that says you can have a law that encryption and decryption is gonna It's gonna be yeah, but you're not necessarily gonna have a law that this is secure against X kind of attack. We would like it to be, and probabilistically it should be, but it's not a law. I can't state it algebraically that if I encrypt two different plain texts. So actually, I can actually get a little bit more formal if we have extra time on symmetric encryptions. So actually, a lot of the ways that computational security, and if you saw my computational security slide way back here, F5, way back. Here's kind of cop-out. Here I could have put a formal definition, but I didn't because I was afraid of time. But the actual formal definition of this thing is, I think if you have some, there's more than one, by the way, because essentially a lot of the times what we're trying to guard against is multiple encryption and as well as chosen plaintext attacks. But chosen plaintext attacks we deal with by PRFs. Usually we are trying to guarantee that for some M0 and then M1 in our message space M, right? We have a game that we call essentially with an adversary, which is essentially our adversary has M0 and M1, and then we give the adversary a kind of encryption oracle with a key, so 0 and C1. So this is going to give us some C0 and C1, which are encrypted with some security parameter. We're gonna consider it implicit. So usually we can denote this as implicit 1 to the power of n. So with the security parameter, the game is this. Essentially, the attacker sends me this. I can, as an oracle, send the attacker back Z0 and Z1, and then the attacker. So it's kind of like a back and forth. The attacker then gives me back a 0 or 1. So that's it. Our 0 or 1 is basically saying, for example, it's guessing is M0 C0 or is it C1, right? Or in reality, what the 0 or 1 is how accurate the guess is of the right ciphertext, right? And it turns out that the security definition of that is that you want the probability of, I believe, our adversary K, for our adversary essentially guessing, I think this has a function. So we usually call this we call adversaries polynomial time. What's it called? Probabilistic. We pretend that they work in probabilistic polynomial time. So polynomial time under some probability. So the probability, if we, what's it called? If we do our game with M0 and M1, I'm probably butchering it, by the way, but this is actually roughly how it is. That the chance of this, so the chance of them, so let's say the probability of this being 1. So basically our challenge, so the probability of him guessing the right thing, what's it called? It's less than 1/2 plus, I'll talk about this. So essentially over 2 different messages, the probability of him guessing the right one is about 1/2 plus some, this is what we call a negligible function. So a negligible function usually is defined, I mean in practicality it's something like we want our negligible function f of n to be some probabilistically, like our algorithm works in like in polynomial time. We would very commonly want this. So to the chance, like the chance of actually, we're like, by the way, an n is our, like, what's it called? Our security parameter, like a key size. Like if we're passing around, what is the likelihood of him guessing the right ciphertext over AES 256? We want this to be essentially 1/2. Plus, yeah?
I think negligible, I just read the definition the other day. I think it's less than all polynomials under the one. It's like 1 over something that's like.
Okay, I think it's like something like less than some e, something similar to that maybe.
But like if it's exactly any sort of polynomial, then it's not negligible. So that's be slower than.
Yeah. Oh yeah, that's it. But essentially the concept I want to get through with a negligible function is that essentially it's gonna make your probability of this be essentially 1/2, effectively 1/2. And so, for example, that is how computational security is defined more formally. And usually, a lot of these things that I carried through, like when I gave definitions of, for example, where are we? Like a lot of, like for example here, when I was talking about gen and h, a lot of these things always have a security parameter. But after a while, we start carrying it around implicitly. Like we start carrying around the hash length is a variable, and that it influences the strength of, essentially, in the likelihood of an adversary like succeeding in breaking our schemes. So this is kind of what I sort of skipped over a little bit when I was defining a lot of these things formally. So similar thing here, like this MAC carries a security parameter because of course the gen does. Because the gen, you see it has implicit security parameter. Actually, a lot of the time it's like it's something like k, it's denoted like this. Gen of something like this. So so our generator, pseudorandom generator over some security parameter gives us some k. So more formal definitions tend to be a little bit more involved. That's about some of the stuff that I skipped. But hopefully, like the core concepts were clear. I also skipped very quickly through, like index calculus. Through the factorization of differences of squares. There's also sieves, which he touched on. But they are really long to explain.
So what did you do in your library? Since you couldn't express that as a law.
Yeah. So I mean, in general, what we could do in our library, if you're designing one, cryptor, is that you simply consider the properties of the functions, and when you're testing against it, you want to test against essentially what are called test of vectors. So for fun's sake, I did a property test over stuff that obviously could eventually probabilistically fail. So for example, I have a property test which is obviously false. But I have a property test over hashes that it's gonna check a bunch of different ones and check that they don't collide. Technically, that will eventually, sometime, maybe before I die, it'll fail a test in CI because it found a hash collision by accident. But in general, for probabilistic properties, you don't really want to worry about those too much because also a lot of those, again, are not, like the one-way functions, they're not even mathematically defined. It's like everything I talked about in the ECDLP, it's like small print if it exists, right? If one-way functions exist, our ECDLP is hard, and we have computationally secure asymmetric cryptography over, yeah.
But I mean, you were saying that none of the like SHA-256, SHA-512, like they're all bad.
No, I never said those are bad.
Okay, I thought because I just saw that. Like,
MD5 is bad. MD2 is bad.
Okay, yeah.
And SHA-1 is broken.
I absolutely misheard because I did see that about like there was a.
I said SHA-1 is broken.
SHA-1,
Yeah, SHA-1 is
but,
broken.
Like that, it was like still an infeasible failure via collision discovered for.
So it's very hard to pull off that collision. I mean, I remember when I read through that paper, it's like, it's not too easy to fabricate. It does require like a certain amount of computational power, which is not like 2 seconds, like MD5, but it is bounded and it is there. So I think once people find collisions in a hash algorithm, tends to be a matter of time until somebody finds a better one.
Right.
But the SHA-2 family is still secure and it's still recommended, especially over KCAC, because it's a lot of the software implementations are straight up better, and we do not currently need to be protected against quantum computers. There are none yet, but the SHA functions are good. If the best resource for the best primitives is this, what's it called? Is this post by a guy called Thomas Ptacek? Yeah. So it's called Cryptographic Right Answers, and this is essentially all the primitives that are not necessarily just because they're hot, but the ones that are essentially as close as you can to proving them being good. So for example, I talked a lot about AES, but the hot one right now is X salsa 20 poly 1305. It doesn't exactly roll off the tongue, but but it's really good, and it's part of TSEC as well, because it's part of loop sodium and part of bouncy castle. So that one is all, like, the reason is because X salsa is a stream cipher and poly 1305 is the authentication function. And they were designed by a guy called Daniel J. Bernstein, which essentially he is also the one that like figured out that twisted Edwards curves, like 25519 would be really good for elliptic curves. So, it talks about this primitive, it talks about symmetric key length. So, usually 256-bit keys. So like symmetric signatures, it's like HMAC is still good. For hashing algorithms, still the SHA-2 family is good. For random IDs, again, DevUrandom. I did not talk too much about random IDs, but just DevUrandom is okay. So when you use what's it called, secure random in Java, or I don't know which one the Haskell equivalent is, but then you just make sure that you have to, in Java you have to feed it native non-blocking PRNG to get DevUrandom, because it defaults to DevRandom. And as you see, NaCl Lipsodium is using the twisted Edwards curves for asymmetric encryption, similar to like the idea of RSA. But there are, by the way, so RSA is only defined up until the size of n, but there are encryption schemes that are made for arbitrary length asymmetric encryption. They're not exactly that useful in practice. So yeah, curve 25519. So asymmetric signatures, 25519 is the same curve. So it's the curve found by Bernstein, and then like I guess they're saying probably nothing, but most of the time people are not using key exchange directly. Like most of the time that's taken care of by TLS. So anyway, Thomas Ptacek is, or I don't know how to say his name, is one guy that I follow on Twitter that is really knowledgeable on this stuff. Another one, sorry.
Also quite
No, but I think he usually has a point. It's not just unnecessarily harsh. And there's also Matthew Green, which is a professor at Johns Hopkins. So he's a good person to follow. And actually, Twitter for Cryptography, funny enough, has a lot of good information. A lot of people retweeting papers. Like you get a lot of interesting, like up-to-date news by just being on Twitter. And yeah, essentially, this page will keep you up to date for now on what attacks you can follow. And then, okay, so let's talk about a little bit of the design decision. So this is just, for example, encryptors. We could talk about password hashers. So password hasher is, again, parameterized over some algorithm A. This is, by the way, a super general pattern that I came across. Because a lot of the things that cryptography takes, that we error check for, I think we could, unless you do something bad, we can have the compiler take care of it. So when you hash your password, it's always going to be a string. Or so technically on the JVM, the most secure way would be taking a character array because you could wipe it. The most common way is a string, but the problem with a string is that the strings are held on the heap and they are only collected by the garbage collector. So that means you are gonna, this is obviously doomsday for Java apps, because in Java apps, unless you're using a hardware security module, you have your keys in memory. But in doomsday scenario, any password that, the moment that you went to the login server, it would be in memory until it gets GC'd. So it's bad because it will leak plain text passwords if you can examine memory. Usually, a lot of people consider that doomsday. Basically, if they broke in, you're pretty pawned. If they have, the privilege to access your application memory ad hoc. So you probably have worse things to worry about. But for example, password hashers simply take a string or the other constructions and return a password hash of A. And you can think about the string as being your key. So this is your keyed hash function, which is in general, well, not in general, but in this case, a key derivation function plus a hash function.
So there's no constraint that A is some sort of algorithm trait or whatever.
Is algorithm. So sorry. In general, we don't add constraints to the trait specifically. We try to leave that up to implementation. Also because it leaves it extensible. The only thing that we could do is add evidence type classes, but in general, those end up being just pollution. If you want to feed in a password hash of integer and not script, I think you have bigger problems than worrying about how it was parameterized. I don't know how you even got a password hash of int or why anybody would go that route, but.
So you specialize it on the function that constructs the password.
Yeah, exactly. So for keys, I have for example for key generators, I can show you. Oh, I think it's so. For example, for symmetric key gen, I have a generate function, which has an f and a k, and it takes some y. And it gives you your key. And then building a key takes a raw array of bytes, and it's going to give you a parameterized f of k. So you can define build unsafe as, of course, just over identity. But essentially, how you can treat this symmetric key generation is by parameterizing it over the effect and making the build function essentially have the effect handle the errors. Because what you care about is if you manage to get a key out of the F, you want that key to be correct, right? And that's how we get a lot of compile time safety. So if building the key passes yielded your key of A or key of Y, then you have a key that has been type checked for length, and you have a key that has been type checked for what's it called? I don't know. Actually, it's mostly for length, just length, but. You just have a type checked key. Now, nothing forces you in Scala to not just cast it. You can literally just cast it to anything. It doesn't matter. If you use as instance of. But we try to concern ourselves with people that are not gaming the system. So if you are constructing your key in a way that is sane, you're going to be fine. And that ends up being a lot of how the development of these things happen, where the generation functions actually are pretty generalizable. You have symmetric keygen, and then you also have asymmetric keygen.
One question.
Yep.
what would the purpose of having both the k and the y parameterized since they're just kind of short?
Well, you have, sorry?
I guess in the previous class or tree.
Yeah.
So you have the k and the y both as sort of separate parameters. But
Yeah.
in the actual type class, it only shows up together. Is it?
Well, I mean, f being our effect that is doing our error handling and whatever, and then k needs to be a higher candidate type that takes one type parameter, because that is how we say that, for example, k is a k of AES 256. So this is a symmetric, like for example, it can be a symmetric key of AES 256. So by having that type parameter, you know that that key is 256 bits long if you constructed it properly.
Yeah, I'm just wondering
I mean, I cannot have it parameterized on the method, I guess. Like that's the thing. It can't be simply parameterized on a method, or else I would need a different type class, which would do the same thing. I cannot be just build of A, because we cannot define, like we can't define A generically without specific constraints. So length, for example. We would need a different type class to handle it. So if we had build and we had, so if we moved this, you're thinking maybe if build was parametrically polymorphic, right?
Yeah, I guess I'm thinking of a simpler thing, and it's possible just to replace.
Oh,
y,
you're thinking about
y
maybe
and k with just a z, and just have an f of z and an f of z as the.
Yeah, I guess it is. Yeah, I mean you could just have k of y. Yeah, you could. There's nothing that really stops you from doing that. I think it's just, yeah. But I mean, the main thing is that I guess in Scala, if you were to make a generic construction, you would have to have them defined like in two places at least at one point. So if I wanted to make, so let's say I'm making all key generators for the AES functions, then I know that it's going to be AES, but it's going to be 256 or something or something. So I am going to end up with 3 parameters at some point. Because I'm going to end up having to apply k to a and then parameterizing it that way. Unless every single one of them has a new type, which we don't want, of course. So at some point, we are going to need this parameter y or a. But yeah, I think that's it. I hope you guys enjoyed the talk. And hope you guys enjoy the rest of your day.